You may have noticed a couple things if you went to the class schedule. So let me do that first. It's kind of a stopgap measure. Chapter 8 notes, we had referenced a file, parasites 8.5, and I hadn't given you that file, so there it is. Again, I'll probably redo Chapter 8 and incorporate it in the notes. I am going to I have edited a few things in Chapter 8, and once I edit a few more things, I'll put a new version up there. I also put, of course, last Thursday's lecture as well as the notes from Chapter 9, which is regression. So what we plan to do today is to look at Chapter 8, the last part, particularly testing the quality of variances, and then also Chapter 9. Now, I gave you a template also for did I not? Oh, I sent you a template for the homework. I may make some changes for that. In other words, some of the ones which actually just give means and standard deviations, I may convert that to real data and let you do more of it in R. The ones that just give the mean and the standard deviations, which was a common practice, in past years because people were mainly calculating these things in these intro courses by a calculator, and so by sort of summarizing the raw data into X bars and Y and standard deviations, then it was relatively easy to do a one sample or two sample t-test and so forth without doing a lot of calculation. Of course, there was a downside to that in that you couldn't really test the assumptions very well, although the one assumption you could test was the equality of variances using the method that I'll talk about today. I will probably introduce a graphical approach also, just like we had a graphical approach to test normality. There are some formal tests for normality also, which is not covered in this book, but those tests suffer from the same problem as the F tests that we'll talk about today for testing equality of variance. That is, the power of the test is not particularly high for small sample sizes. And so there are some better techniques, I think, for looking at equality of variances on a more heuristic way of doing it, at least, but it's actually very effective. So I'll probably add that in at some point to show you a graphical way of looking at the assumption of equality of variance. And at the same time, it lets you look at normality for both groups. And so it's a fairly effective method for assessing both normality and equality of variance. Now, so I don't know if I'll need this again. I don't think I'm going to need it. Anyway, if you want to download, Chapter 8 has not changed. As I said, when I do change Chapter 8 notes, I will send you an email letting you know that there's an update. There's several things that I want to update. But you might want to download that parasites file and then upload it so that you can sort of fill in one of the commands in, or one of the functions, I should say, in Chapter 8 notes. And you should also download Chapter 9 notes. So you might want to do that now. So if you want to follow along with me, you can do that. So I'm going to go into our studio now. And I have Chapter 8 already loaded. What I want to do next is I'm going to set the working directory. That's not what I wanted to do. I got to go to the correct place. Chapter 8. Okay. This is where I want to be. I think the data set should be okay. Now I'm going to set the working directory to Chapter 8. I'm going to go ahead and knit this so we can just quickly review some of the things we did before, that I plan to focus primarily on the last part of Chapter 8. So there are a few enhancements we could do here. When we have a single sample, as we do here, and this is a very small one, only 12 observations, this is the miles data, miles until you hit the wall. It was hypothesized it was 17. And so that's the histogram. Now, one of the problems with the histogram is that how you choose the boundaries, for example, can greatly affect what the shape of the histogram looks like, particularly with a small sample size. So if you're assessing normality when you have a small sample size, that's not a real good way to do it by looking at the histogram. So the normal probability plot is much better. Now, what I should do, and I will do, is draw a line through that, because what you're trying to decide is whether or not that's a straight line. And so we could add a command in R that would draw a straight line through that. Now, the problem is that if you had an outlier, you'd have one observation, maybe that highest observation, that would be way off the scale. And so if you tried to fit a straight line using what we're going to do in Chapter 9, which is least squares, the outlier would greatly influence the fit. And so we don't want to do that. And so what we usually do is we fit a straight line through the two quartiles. 2 points determine a line, and the quartiles are fairly stable. So in other words, the lower quartile or the 0.25 quantile and the upper quartile or the 0.75 quantile. If you identify those 2 points, you can plot a straight line through them, and that line will be robust in the sense that outliers, or even some skewness, will not greatly affect the quartiles. So when we draw a line, we're not going to do the normal way of fitting a line to the data. We're going to fit the line through the quartiles, and that will be what's called a robust fit. And that gives us a better way of assessing whether or not we follow a straight line, since we can look at the deviations from that line. So I'll add that line. What I did next is I did a one-sample t-test, and I did confidence intervals. And what I first of all did is I did it by hand, and then I just used the function t-dot test on miles and mu equals 17 as a hypothesized value. And of course, that's much easier. The purpose for doing the other calculations was just to show you that, in fact, you can use R to compute all the quantities, and you get the same results, of course. Now, I've decided that I don't think I'm gonna either give assignments for or talk extensively about the non-parametric. What's in the book is equivalent to what we've done here in terms of the Wilcoxon sign rank test for a single sample, for example. This is done in the book, but it's done a little bit differently. One of the things you can do is get a normal approximation, which is what they do in the book, and therefore you can use the normal distribution to make inferences. Again, at some point I'm going to bring this into accordance with the R way of doing things. But I don't think I want to focus too much on non-parametric tests. You should know about them. You know what they are. Here's how you do it in R. It's very simple to do in R. So if you did a one-sample t-test, it's very, very simple to just say, okay, what is the Wilcoxon sign rank test? And you can do that in one R statement, and so it's quite easy to do. I do want to mention just one thing, though, about the non-parametric test, is people sometimes call it distribution-free. Well, it's distribution-free, sort of. Here's the thing. When you say distribution-free, or if you say non-parametric, you say, well, it doesn't depend on a parametric distribution. It's true that we're not assuming normality. We don't have to assume normality, even for a small sample size. But we do need to assume symmetry. So that's actually a fairly strong assumption. Not as strong as normality, but we have to assume something nonetheless. And a lot of people think, oh, if I don't have normality, I can just use this non-parametric test and everything will be okay. Well, the problem is we still assume symmetry. So if the problem is that you have a skewed distribution rather than a normal symmetric distribution, then the Wilcoxon-Simon rank test may not help you that much. So keep in mind that if you do use this non-parametric test, it doesn't mean there aren't any assumptions. It just means the assumptions are a bit weaker, but they're not that weak. So you have to be a bit careful. Then we went into the matched pair test where we actually compared, we're matching. In other words, we have like repeated measures where you have the same experimental unit measuring like before and after. That's a very common situation where you have a test and you get a before test and an after test for each student. So it's not as if you have a different experimental unit for the before group and the after group. You have the same person taking the before and the after. This is another common type of paired type sample. And so in this case, we do a paired t-test. And well, if we just take differences, we can do a one-sample test on the differences. And there are a couple of ways you can do this using R. I could use t-dot test, which is what we did above, just on A minus B, which does it on the differences, and that's one way. But you can also do t-dot test with A and B as arguments, and then you say paired equals true. And so that might be a little bit more transparent as to what you're doing, but again, you can do it either way. And then here's again, the Wilcoxon matched pair, which is really just doing it on pair data, which is like taking differences. And then we talked about the two-sample t-test, and I just want to point out that we have two groups, and for the small sample size, we're assuming that the observations are independent, that both populations are approximately normal, and that the variances are equal. And so we have a chemical example. We had a chemical example. We had a control and a treatment. And so we get the means and the standard deviations for the control and the treatment. And by the way, I prefer to use subscripts that refer to, in other words, mu sub c and mu sub t, rather than mu1 and mu2. And the reason I prefer that is because if you're doing a one-sided test of something, if you use mu1 and mu2, you say, well, which one's 1 and which one's 2? And it starts to make a difference in certain cases. And so I prefer using meaningful subscripts rather than just always 1 and 2, which is what the book used. In this case, we do have a one-sided test because notice when we do this, we're going to use t-dot test, and we have control and treatment, but we didn't say paired equals true here. But we did say var dot equals true. In other words, this is saying, I want this t-test conducted on the assumption that the two variances are the same. And also, it's a one-sided alternative. It's a one-sided alternative. So you're saying that mu for the controls is less than mu for the treatment. So when we carry out this test, we see that it's not actually significant. And we accept the null hypothesis. So what I wanted to talk about today a little bit more, and I realized in the book there's there may be some confusion between how the book does things and how R does things. And it's a simple reason. Up until now, we've been dealing with the Z distribution and the T distribution, at least in terms of inference. And so, mainly the T. It's a symmetric distribution. So if I'm looking at the upper 5% and I want the lower 5% quantile, then it's just minus the upper. Now the upper, the way R thinks of the upper is the 0.95 and the lower is the 0.05. But the problem is, in the back of the book, they only give the upper. And when they say T with a subscript 0.05, it doesn't mean that's what's less than, and it means that's what's greater or to the right. So in other words, the tables in the back of the book, where whether it's the T, the Z, or the F, give the upper tail, and the subscript refers to that probability of an upper tail, whereas R does exactly the opposite. It's giving the cumulative distribution function in essence, and so what it's doing is it's giving the probability less than or equal, whereas in the back of the book it's probability greater. Well, this causes some confusion. And it particularly causes confusion here with this F-test. And so let's take an example where we're looking at the number of echoparasites between rice and rats. And so we are going to actually count these parasites. And in the book, they have a side-by-side stem and leaf plot, and they also have a box plot, which I also have. I do not have. There is a way to do stem and leaf plots in R. Maybe I should put it in here. But so we do a stem and leaf plot in the book, and then the box plot is probably more informative. In fact, if I look at the box plot here for the rats and the mice, as you might expect, there are more parasites on the rats than the mice. They're bigger. But that's not all. What else do you see? Well, it's more spread out. And the widths are proportional to the variances. So, in other words, there's not only a bigger mean, but a bigger variance. Now, whether or not the mean is proportional to the variance, if it were, what distribution would we be talking about? Poisson. After all, we have counts, right? We have counts. And for the Poisson, the mean equals the variance. And so if the mean gets bigger, the variance gets bigger. So you might think that we have a Poisson distribution here. And so perhaps we should be making inferences using a Poisson. And in a more advanced course, for example, the categorical data course, you would learn how to do a Poisson model that would actually allow you to fit the Poisson distribution. So if you go ahead, there are several problems that if you go ahead and fit this using an assumed normal distribution, it appears that not only is the variance greater, but there are some outliers. Those circles at the top, and there's one at the bottom for rats, indicate outliers. When I say outliers, I mean they're greater than what you would expect if you had a normal distribution. So if you actually did, on this example, I should add maybe a plot that shows you what if you did a normal quantile plot for each group. Now, ideally, what you would like to do, and this is a little trickier, you'd like to actually have both groups on the same graph for the normal quantile plot, and you would like to be able to draw a straight line for both. Now, we know if there are straight lines for each group, that means normality is correct. But it's also true that the slopes of the lines indicate whether or not the variances are the same. So if I did normal quantile plots in which I put both on the same graph, and I draw the lines, then the straightness of the lines and the slopes of the lines are a good way for me to look at the assumptions for this two-sample t-test. Now, what we're interested in testing is we want to test that the two variances are the same. In other words, that sigma for the mice, or sigma squared, it doesn't matter, for the mice is the same as sigma for the rats. Now, there's a whole class of what are called apply functions. So there are certain things that we need to compute, and I'm going to compute it this way, but again, I'm going to show you there's a simple way to get this test. So going back to the raw data, but this is where you had a problem. Read.table, parasites 8.5.text, header equals true. When the header file, when you have the column headings on it, and you want those to actually be the variable names, then you say header equals true. So the file I put up that you can download, you can load this way, or you can simply cut and paste it in do it, for example, the way I did here. But that would involve a little bit of effort. Well, there are various functions on what are called the apply. There's a whole group of OR functions called apply. There's apply, there's sapply, there's tapply. There are various ways of using the apply function. And what we're going to say is that we have I think at this point, maybe I'll go back here and take a look at this because we can throw in a few more things. I can find the beginning of this. Okay, so I just wanted to show you one thing. So if I read it in and I look at the first 5 observations, I see this, and then I say, I want to show you another command. So if I say search, this is my search pass. If I say a name, it will search to find that name. And so it finds the name. I mean, how does it find the name parasites? Where is parasites? Can anyone tell me? The parasites is in the global environment. And if I actually go to the workspace, you'll see that parasites is here. I didn't clean this out from the last time, so let me clean it out, and let me clean it out. Okay, now I'm going to re-execute this. Now, when I re-executed this, I created a variable called parasites, right? And automatically, parasite appears in my global workspace. I'm looking at the global workspace. And then, if I run this, those are the first 5 observations. I could also have simply said head of parasites. Did I misspell something? And the head will give me the first 6 observations. So instead of saying 1:5, in other words, I have an operator called the square bracket operator, and that actually is going to allow me to subset. In this case, it's a data frame. In other words, if I say the class of, let me try to type a little bit slower. Parasites is what's called a data frame, and if you're familiar with SAS, this is like a SAS data set, or if you're familiar with JUMP, it's like a JUMP data table. Or its corresponding entity is a data frame. Now, the data frame is different from a matrix in the sense that a matrix, everything has to be of the same type in a matrix is sort of square, like a data frame. It's just that everything has to be of the same type. In other words, if it's numeric, everything in the matrix has to be numeric. If it's character, everything in the matrix has to be character, and so forth. But in this case, notice that the first column is in fact have letters. In fact, that's a factor, and the second column is numeric. So the 2 columns are not of the same type, and that's allowed in a data frame. But within a column, they have to be of the same type. So you can't mix character and numeric within the same column, but different columns would be character and numeric. And that's, in fact, what we have here. Now, you might also say, suppose I type in rodent. What's going to happen? Can anyone tell me? What? It is the first column, but what's going to happen if I hit return? Right, but will it find it? The only reason it found it is because I had previously done it. If I had not done that, it would not have found it. So what happens is I had previously attached it, and I didn't detach it even though I eliminated it from the workspace. So in other words, if I now run attach, okay, I actually perhaps shouldn't have done that again. There's a detach command I perhaps should have run. It actually attached it a second time. It didn't know that it was really different. So if I say ls2, in other words, this is where it finds parasites with a capital P, and it's not the same as the data frame parasites with a small p. And here's a rodent. In other words, I should have done this in a different order, and I could have shown it more effectively. In other words, when I created something called parasites, if I would have not attached it and tried to run this command where I say tapply parasites rodent mean, that would not have worked because it would not have been able to find parasites or rodent with capitals P and R because they're not in the global path, they're in here. And previous, maybe I should try to emphasize this a little bit more. Let's see why. Yeah. Okay. Let me start this again. I'm going to wipe this out right here. I'm going to start this again because I want to sort of illustrate something that's pretty important. Okay, I read in parasites and I put it in our object, which is a data frame called parasites with a small p. So therefore, this appears in my global workspace. Now let me do a search. Oh, gotta watch that. Okay, what happens now if I type in rodent? It doesn't find it. Why? It's not in the global environment. This is what's in the global environment. So where is it? If it doesn't find it here, it goes to here and looks. If it doesn't find it here, it goes here. These are mainly packages, but packages have data. So you might find things in certain packages. And in particular, there's a package called datasets. It has lots of datasets in them. And so if you haven't found it, and you know it's a built-in dataset like cars, eventually it will find it down here in the package : datasets. So it will find it if in fact it's a built-in dataset, because that's all of these things by default. Well, except for the second one, which is a bioconductor type installer. And then RStudio gets installed automatically when you run RStudio because it's some utilities that RStudio needs. So how do I find the variable names? Well, there are two ways you could do it. I'll show you what you can find. Parasites $rodent. If I do that, it finds it. In other words, if I take parasites and I have a $ with a rodent, it extracts the data from that R data frame. So I can get it that way, but it's a nuisance to have to write parasites $ variable name, parasites $, parasites with a capital P. It's a nuisance to do that. So a better way is to simply attach it. So if I attach, and now I do a search, now parasites is in the second position. Well, how do I find out what variables are in the second position? Well, the ls command, again, will do it, except I put a 2 here. And that says in this second position, this is 1, 2, 3, 4, 5, so on. In the second position, these are the names of things I can access. And once I've done that, all I have to use is the names. So this is kind of an important R thing to realize. And so now, when I run this command to get the means, it knows where to find the parasites with a capital P, which is actually the variable name, as opposed to parasites with a small p, which is the data frame name. Is that clear? R is case sensitive. Parasites with a capital P is different than parasites with a small p. In this case, they're very different. Parasites with a small p is a data frame. Parasites with a capital T is, in fact, it's like a vector because it's actually one of the columns in the data frame. So this mapping function says, I want the mean of parasites, but I want to map over a rodent. So what I'm saying is, I want the mean for each of these, of which there are 2, M and R, for mice and rats. So I want to get the mean by rodent. Now there's another way to do it. There is a by statement in R. And if you've ever used SAS, you know by group processing is very, very... Have any of you had a SAS course or know some SAS? So by group processing is very common in SAS. If you haven't had it, you may take 521 and 522 at some point, and you'll see that by group processing is one of the features of SAS that's commonly used. So at this point, we've computed the means. And then when you compute the box plot, one of the things that you generally need to do is sort of blow it up so you can actually see the graph. And that's what we had previously. And now we can compute the variances. By putting the parentheses on the outside, not only computes it, but it prints them out. So let me get rid of the graph here. And then I can get the sample sizes by using, I'm going to map the length. I'm going to get the length of parasites by rodent. And then I'm going to get the degrees of freedom. Now it turns out that if sigma 1 squared equals sigma 2 squared, that means under the null hypothesis that the ratio of sigma 1 squared to sigma 2 squared is 1. And so our test statistic is going to be S1 squared divided by S2 squared. And if the null is true, we expect that to be about 1. If that ratio is a lot less than 1, a lot greater than 1, we're going to reject. Now, if you're estimating sigma squared, a single sigma squared, by a single S squared, in other words, if you take if you have a single group and you have a sample variance, that estimates the population variance. So the sample variance, S squared, estimates the population variance, sigma squared. And how many degrees of freedom does that have? Well, if you don't remember this, look back on the book on chi-square. S squared, under normality, is approximately distributed as a chi-square distribution with the sample size minus 1 degrees of freedom. So it's n minus 1. Well, in this case, I have 2 of them. I have 2 variances. And the first one will have degrees of freedom in 1 minus 1, and the second one in 2 minus 1. And the F-test is a ratio of variances, and it will have numerator and denominator degrees of freedom. So there are 2 sets of degrees of freedom. And you may need to read the book to get a little more detail about this, but there are 2 degrees of freedom. So when we do an F-test, we have to have a numerator degrees of freedom and a denominator degrees of freedom. And that's what I'm computing here. In other words, which I call nu1 and nu2. In other words, nu1 is equal to n1 minus 1, and nu2 is n2 minus 2. Now I used vector notation. When I computed p sub n, it was a vector of length 2 because there are two types. there are two types of rodents, rats and mice. And then what I'm gonna do now is compute my f-test, which is just the variance of s squared 1 over s squared 2, and so I do my f-test. So when I do this, I'm going to compute the degrees of freedom, and then I'm going to do my f-test, and then finally here's my f. Now notice my f is 0.3. What does that say? That says the variance of the rats is greater than the variance of the mice. Well, we saw that from the box plot, right? And so, since that is true, well, is it significant is the next question. Okay, it's 0.3, so it seems like that it's quite a bit bigger. It's like 3 times as big. But is it significant? So we need to do an f-test to test for significance. By the way, I gave a names argument at f-test, but I'm now going to remove it because if I don't remove that, it shows up in odd places. So I'm going to assign the name of f back to nothing. Okay. Now, if I were doing an f-test, I would say, I get an f, I compute an f, and I ask, is it in the, suppose I'm testing at alpha equals 0.1. And you might want to use 0.1 rather than 0.05, and the reason is this f-test is not very powerful. So what happens if I increase, alpha is the probability, what is alpha? It's the probability of what? It's the probability of a type 1 error, right? We usually denote alpha, probability of type 1 error. So it's the probability that I reject when in fact I shouldn't. That is, it's the probability the null hypothesis is true, and I say that we reject. So I want that to be small, but how small? Well, what's the relationship between power and alpha? Well,
when alpha is the smallest.
The smaller alpha is, what happens to the power? Well, put it another way, as alpha gets bigger, what happens to the power?
If alpha is bigger, then null is rejected.
Yeah, if alpha is bigger, it makes it easier to reject if alpha is bigger. So your type 1 error is bigger, it's easier to reject. But correspondingly, the power is when you reject when you should reject. Okay, and it increases the power. If the distribution if you have a distribution and you've got this upper tail, let's say, or the lower tail, and it shifts, you're going to actually have more probability in that upper tail. And so the end result is if I make alpha bigger, it increases my power. You're losing some on the type 1 error to get better type 2 error, or better power. So I made alpha 0.1. There's a lot of discussion in environmental studies about what alpha should be in environmental studies. And the reason is that a lot of times, let's say you're in oil industry and you do an oil spill and you say, oh, there's no difference. And so, yeah, so you test these things and it comes out, oh, there's no difference. And so the problem is that if there's a fair amount of variability, you've tilted it in favor of the null too much. And so there's actually a lot of discussion, in the environmental literature about what alpha should be. And a lot would argue that choosing alpha too small, it makes it convenient that you make it hard to reject, too hard perhaps, and you have low power. And so by making alpha a little bit bigger, by making alpha the significance level bigger, I can make the power bigger. And so that's sort of the argument that in some cases, we know the f-test doesn't have much power, so therefore I'm going to make the alpha level 0.1 so that I have a little bit more power at least. So let's see what happens. Now, what I'm going to do next is I'm going to compute the quantiles of the f at the 0.05 and the 0.95. Now, if I look at 0.05 and I'm looking at the probability I'm less than that, well, I'm not looking, I'm looking at the probability I'm less than that, or I'm looking at quantile, which is I'm actually finding a number that has 0.05 less. And then for the upper tail, I'm finding 0.95, which is a number that has 95% less or 5% greater. Then those are my, what are called the critical values. And if my f falls outside of those critical values, then I'm going to reject. If it's inside the critical values, I fail to reject. So what is my f? My f is 0.3, and my critical values are 0.32 and 2.26. Does it fall inside or out of the critical values? It falls outside of them. On the lower end, it's less than 0.32. It's 0.3 something. So what is my conclusion? My conclusion is I reject, and I conclude that the variances are equal. But notice I didn't reject by much, and notice that I used a alpha equals 0.1. Would I have rejected had it been a 0.05? Well, we'll see in a minute. So what I want to do next is compute the p-values. Now this becomes a little bit tricky. The p-value, which is line 198, it's the probability I get something as extreme or f or bigger. Well, if you have a symmetric distribution, it's pretty easy to do. You can say, you can take the absolute value of the test statistic, and then you compute the probability you're greater than that, and then you can double it. That's for a symmetric distribution, but this is not symmetric. Now, there's a discussion in the book that would say, okay, I get an f, and in this case my f was less than 1, so part of what I need for the p-value is the probability I'm less than or equal to f. So this first part is the lower tail part of the p-value. But I can't get the upper tail by just doubling it because the f is not symmetric. So in order to get the upper tail probability, this looks kind of strange. I'm taking 1 over f, and I'm reversing the degrees of freedom. Now that's equivalent. If I look at my f-test, which is s1 squared over s2 squared, if I wanted the upper tail, I could actually flip that and put s2 squared on the top with s1 squared on the bottom and flip the degrees of freedom. And that's in essence what I'm doing to get this upper quantile I'm getting the p-value for the upper, is I'm taking 1 over f and flipping the degrees of freedom and subtracting that from 1. And so it's a little bit tricky. There may be another way to compute it, but this works. So let's see what the p-value is. It's 0.079. In other words, what would have happened had I set alpha to be 0.05 as my significance level? I would have failed to reject because my p-value is greater than 0.05, but it's less than 0.1. So I would have concluded at the 0.05 level that I don't reject, and at the 0.1 level, I say I do reject. So it makes a difference. In this case, it very much makes a difference. Now, we know that we have a problem in that we have small sample sizes. We know this f-test is not particularly powerful. And so the p-value tells us, it tells a story. It's 0.07 something. And so at that point, you have to kind of make up your mind. But the problem is when I go back and look at that box plot, I'm a little bit worried about this assumption. In other words, the box plot would make it hard. The box plot would make it hard for me to conclude that those variances are the same. Now, how much does it affect the t-test? Well, we can see a bit. Now, by the way, we consider 90. I'm going to put a little bit more. I'm going to write out some more things here for you before I update this, because this is a little bit tricky. Because again, it's using this 1 over f. for the quantiles in order to get the lower and upper limits. And I'm going to sort of show you a little bit of why this is true. So maybe for now, sort of take my word for it. I'm going to fill in some words here to try to explain this. It's sort of explained in the book. I don't think it's very good. So I'm going to try to show you a little bit more of why this is true. What I'm trying to do is get a confidence interval on the ratio, on sigma 1 squared over sigma 2 squared. I'm trying to get a confidence interval on that. And so we get if you're getting a confidence interval on mu with a t-test, you know that that's pretty simple. You just take y bar plus or minus the t-value times the standard error of y bar. Why? Y bar plus or minus the t-value times the standard error of y bar. It's plus or minus. It's very simple to compute because of symmetry. This doesn't have symmetry, so I can't compute the lower and the upper limits of my confidence interval in quite the same way. So I'm going to show you a little bit more about how this is calculated. And when I update the notes, I will put that in there. So the lower limit is actually 1 over the f at 0.95, which actually corresponds to the 0.05. And so I'm taking it times the f. In other words, it's not plus or minus. And that's why it's going to take a lot of hand waving to sort of convince you of this. So what I'm going to do is put a little bit of algebra in, and hopefully that will convince you that it's f times, not f plus or minus, it's f times these quantiles. And so I'll show you where that comes about. But at this point, what I'm doing is computing an upper limit and a lower limit, and the upper limit's pretty straightforward. It's the 0.95, but again, there's a reason why the degrees of freedom flip. And that is that it's S1 squared over sigma 1 squared divided by S2 squared over sigma 2 squared, and because of the ratios of the ratio, the sigma 1 squares and the S squares sort of flip signs as you flip them around, if you think about it. And therefore, you get this inversion of the degrees of freedom. But again, instead of trying to sort of talk around it, let me just show you. Sometimes algebra is better than just words. So at any rate, I'm going to compute these two limits, and I will explain. I'll show you what the algebra is for that, and then we can talk about it. So these are my confidence limits. Now the good news is that R has a test called var dot test. Now let's hope that we get the same answers. So here's the var dot test, and we see the f is 0.3 as we computed it, right? And we see the p-value is 0.079 as we computed it. I showed you how to compute it. This, of course, var dot test in R just does it. And the 90% confidence interval is 0.1324 and 0.92, which again is what I computed for what I called L and U for lower and upper. So you can see that we replicated everything here. The ratio of the variances is the f-test. So in practice, it's a pretty simple thing for you to do. I specified the confidence level. If you don't specify it by default, I think it uses 0.95. So again, you can always go into R if you're uncertain of these things. You can always go in to help, and if we type var dot test, that's not what I wanted. If we do var dot test, we can see what the arguments is that you have x and y, which are the numeric vectors that I'm concerned about, but it's not the way I did it. Notice I did it as parasites tilde rodent, which was one of the ways we could do a two-sample t-test, and that's actually more convenient. The tilde means as modeled, parasites as modeled as rodent. So I have two levels of one factor affecting what the parasite responses might be. And to me, that's a little bit simpler, just because of the way we had our data. It's simpler. Notice that the ratio is 1. That means the null hypothesis is 1. The alternative could be two-sided less or greater. So we could do a one-sided test. We could test sigma 1 squared is greater than sigma 2 squared. And the confidence level by default, as you see, is 0.95. So again, a lot of times when I'm working, I'll sort of work this way so that I can bring up the help file on this side to help me on the right, to help me code on the left. Are there any questions? Well, now, so we rejected, albeit we rejected at the 0.1 level, not the 0.05 level, we rejected. So suppose can we do a t-test assuming that the sigmas aren't equal? Is there a t-test? Yes, there is. It's called the Welch test. They don't call it that in the book, but that is, in fact, what it is. It's the R calls it the Welch test, and it is the Welch test. And what it does is it assumes that we're going to do a t-test. What we're going to do is we're going to do a t-test, what I call adjusted t. And instead of pooling the variances, what we did when we assumed the variances were the same, we pooled the variances. And when we did that, that was the standard t-test, assuming that the sigmas are the same. In this case, notice that the formula, the adjusted t, takes the p mean of 1 versus 2, takes the square root of the sigma 1 squared over n1. That's what this part on the right is, where it says the square root. That's s1 squared over n1 plus s2 squared over n2. In other words, we did not pool. The problem if we do this test, it's not t exactly. So what we have to do is adjust the degrees of freedom. Because the degrees of freedom for the two-sample t-test is what? Yeah, it's n1 plus n2 minus 2. The way you get that, you have two estimates. One has n1 minus 1, and the other one has n2 minus 1. If you add them together, you get n1 minus 1 plus n2 minus 1. It's n1 plus n2 minus 2. Well, that's not quite the degrees of freedom. Here we have to, there's a very complex formula. It's in the book, and this is the version in R. You can adjust degrees of freedom. And so when we did the I was looking for the sample sizes. I think it's 31. Wait a sample. Yeah, 31 and 9. So that's 40. So if I were doing a t-test, that would be 38. However, let's do the adjusted t. Now this is the t-test. This is not the f-test for variances. I'm now back to the t-test. And so if I look at and I'll put a name. If I look at the actual adjusted t-value, it's a minus 2.85. And the adjusted degrees of freedom is 24.8 roughly. Now, if I run this, you notice I just computed it sort of by hand, but if I do parasites tilde rodent with the t-test, by default, it does the Welch test. And notice that it's minus 2.85 that I just computed. That was my adjusted t, and the degrees of freedom is 24.78. So let's take a look here a minute. Now you notice that var.equal equals false is assumed. So if I go in here, just as a point of comparison, and I do this t-test, but I'm going to put comma var dot equals true, let's see how different it is. You notice the degrees of freedom is quite different. As we said, it was 38, not 24 point something. And how does it differ in terms of the p-value? In other words, they both are negative. This is a minus 2.85, and when I assume equality, which is arguably not a good assumption, it's a minus 2.09. Notice that the p-value here, we barely reject when I assume they're equal, we barely reject. It's a 0.044. But notice the p-value when using Welch's test. Even though the degrees of freedom is less, I have a much smaller p-value, 0.0086. So in this case, at the 0.5 level, I rejected in both cases. If I would have been testing at the 1% level, that is a 0.01, I still would have rejected. In other words, if you want to really cut down your significance level, that is your type 1 error you want to make small, and you had a 1% test, I still would have rejected with Welch's, but I would not have rejected using the assumption that the variance is the same. So my point is, in this case, it's very, very questionable that the variances are the same. And we see we could have gotten a difference depending on the significance level. In this case, we have high significance with Welch's test, and we still squeaked down to 0.05, but it's not an overwhelming rejection. Yeah.
So in this case, when I'm interpreting the result, we should use the first Welch test, right?
In this case, if you're really, unless I'm really confident, it's so easy in R to do both. Okay, it's so easy in R to do both that, why not do both? You could also do the two-sample nonparametric test, two-sample Wilcoxon test. But again, that assumes symmetry, and we can kind of look. There are graphical ways to look at symmetry. In other words, if you want to say you're not saying is it normal, which you can do with a normal probability plot. If you want to say is it symmetric, there are ways to plot that to answer the question, is it symmetric? I haven't shown you how to do that. Maybe at some point I should throw that in. So we can test the assumption of symmetry by graphs. We can also test the assumption of variances being equal by graphs. And a lot of times these graphical methods are better than the formal test. The reason is we're very good at picking out patterns. But we don't have a significance level, and people feel comforted by having a p-value when they do a test. But what the problem is, the power is not great. So you get this false sense of security. So they say, oh, no problem. No problem. I can assume the variance is the same, not realizing that the power is so low that you almost always say they're the same, even if they're quite different. Okay, just for point of reference, let's do the Wilcoxon test. And we can say the Wilcoxon test is sort of between them. It has a smaller p-value, but it's closer to the two-sample t-test, assuming the variances are equal, than it is Welch's test, which has a much smaller p-value. And the reason might be because maybe symmetry is not such a good assumption. So these are all things to keep about. A lot of people they'll know a little bit of statistics, what they call a little bit enough to be dangerous. And so they run lots of t-tests, and a lot of times it isn't a t-test you should be running at all. But let's assume that it is the correct thing to do, but you run a t-test in, you put it in, you get it out, everything looks fine. You haven't checked the assumptions. And you always should. Any questions before we move on to 9? Okay, well, we're going to start chapter 9 now. At least we'll get sort of into it a bit. So I'm going to go back and look at my notes, and I'm going to bring up chapter 9, which is on regression. And here's the RMD file. This is the file, and I'm going to set the directory to chapter 9. So let's take a look at this. I'm going to knit it. So I'm going to talk about this a little bit first, just to give you an introduction. So what we're talking about is if we have some data, we want to fit a straight line to it. And people have probably been doing this for a very long time. And initially, what people probably did is sort of what you call the eyeball method. You try to just draw a straight line that looks like it's right. There are lots of ways you could fit a straight line for this. If you take the vertical deviations from each point to the line, you take the vertical deviations, and I think in the book they may have a graph of that. If you squared up those if you took the vertical deviations from if you drop a line from the point to the line, or if you go up if it's below the line, but the lines are not perpendicular to the regression line, they are perpendicular to the y-axis. So I'm dropping a line straight down or straight up. Does that make sense? If I then squared those segments, and added them up, I would want, if there was a really, really good fit, those sum of squares, those are actually called residuals, the sum of squares of those residuals would be small. If the points were right on the line, then the deviations of the points from the line would be very small, and that would be good. In this case, that's not the case. But you might argue that given the spread of that data, that's not a bad fit. And in fact, that's called a least squares fit. By least squares, I mean that I find the slope and the intercept of that straight line such that the sum of squares of those residuals is minimized. So let me look at it in a slightly different way. So we're going to look, we're going to have this sample, and we're going to have paired samples. We're going to have an x and a y. Now, x we're going to call the predictor variable, or the explanatory variable, or sometimes we call it the independent variable. Y is the outcome variable. Sometimes we call it the dependent variable. Now, independence and dependence have other means in statistics, so people have shifted a little bit towards saying explanatory variable and outcome variable. But at any rate, suppose you have age and systolic blood pressure, which you're going to measure on patients. So for each patient, you measure their age and the systolic blood pressure. And then you plot it in what's called a scatter plot. So at this point, if you plotted it, you only have the points, not the line. So you get what's called a scatter plot. Well, that can be pretty informative. But what I want to do is predict the systolic blood pressure can I predict the systolic blood pressure from the age? That's the question that I'm asking. So I have a model given here. Y is equal to alpha plus beta x plus epsilon. What this says is I have a straight line where the intercept is alpha, the slope is beta, but I have this epsilon term, which is the error about that line. Now, technically in regression, we're assuming x is fixed, and the only thing that's random is the epsilon. But in reality, in most problems, both x and y are random, and we consider the problem a conditional problem. Now again, alpha is the intercept, that is the value of y when x equals 0. Beta is the slope, it's change in y for a unit change in x. And epsilon is the random deviation about the regression line for a given x. And we're assuming that's the same no matter what the x. In other words, if at a given x, I sampled a whole bunch of y's, they would have a spread, and the variance of that spread would be sigma squared. If I go to another x and sample a whole bunch of y's at that same x, I would have a spread, and that spread is still going to be sigma squared. Now the problem is I don't know alpha, I don't know beta, and I don't know sigma squared. I have to estimate them from the data. In other words, alpha, beta, and sigma squared are what we call parameters, population parameters. We use Greek letters typically to represent population parameters. We don't know them, and we won't know them unless we get an infinite sample. And then we estimate them by Latin letters. So What happened when we had the one sample t-test? We had mu. Mu was the population mean. Y bar was the estimate of mu. It was a Latin letter. Sigma squared was the population variance. We estimated by S squared, again a Latin letter. So the samples, we use Latin letters, whereas Greek letters are used for the population. That's typically true. There's some exceptions to that. So what I want is a line I'll call y hat. The hat means predicted value of y. And then my A I'm going to use as my estimate for alpha, and B I'm going to use as my estimate for beta. But how do I get A and B? Now you remember those vertical lines I was talking about? Let's go look at this graph a minute. Let's just take a particular point right here. The vertical line is this line straight down to here. Here's, at a given x, this is the y hat, and this is y. So y minus y hat is the residual. And I'm going to square those and sum them up. That's precisely what I have done right here. So this is the sum of squares of residuals. Now y hat is equal to a plus bx, and if I substitute for y hat, if I substitute right here for y hat, a minus bx, what I'm really saying is that I want the sum of y minus a minus bx squared. I want a and b that minimizes that. Now this course is not assuming calculus, but I will just say this. If we take derivatives with respect to a and with respect to b, and I set those derivatives equal to 0, and I solve for that, it will solve those equations. Now it turns out, because that's a quadratic equation that has a square, when you take derivatives, you get a simple linear, you get a linear set of equations in two unknowns that are linear, and it's very easy to solve. These are called the normal equations. So if you did, now again, you need to know sort of how to compute these, but you don't need to know how to derive them in this course. But for those that do, you simply take the derivative with respect to a, derivative with respect to b, set both to 0. You get you get two equations and two unknowns. It turns out they're linear. And back in 6th grade, you solved linear systems equations. Maybe not big ones, but you had little things where you used substitutions and subtractions. And that was something really you do maybe 6th or 7th grade. Maybe it was 8th grade. I don't know. But at any rate, it was something that was previous to high school, in my case at least. And so it turns out that we can solve those normal equations for a and b. And if we do, we get these formulas here. It's called the sum of corrected cross products in the numerator. In other words, you take x minus the x bars. And the book steps through how you calculate this. So if you want to see an example of where you actually step-by-step do it by hand, it might be worthwhile looking at the book. So it's the sum of squares of corrected cross products for the numerator, what I call s sub xy. In the denominator, it's sort of like a variance, right? It's x minus x bar squared summed up. But I didn't divide by n minus 1. On the top, likewise, I didn't divide by something dependent, n minus 1 either. So this second group of formulas right here is simply algebraically equivalent to this first one. And if you were doing it on a hand calculator, this second group is easier to do by hand than this first group, because the first group requires you to subtract for each element, take the difference, and so forth. So it turns out that the second group is easier to do than this. The second term is easier to do than the first term. And that's because you can often get a sum and sum of squares in a lot of calculators simultaneously. So you don't have to enter the numbers twice. So there are a lot of calculators that allow you to do this very simply. So it's simply that ratio, s sub xy over s sub xx, and then a is y bar minus b. Once you have b, you can calculate a as y bar minus bx bar. So let's just take a quick look. I'm going to create a data frame. I didn't read it in this time. I created a data frame. I said I'm going to name the components of the data frame. Age is the first component, and there's the data. Systolic BP is the second component. And I'm going to print out the first 4 observations. You notice that 1:4 that says print the first 4. And then I'm going to attach it so I can reference those two names. And I'm going to compute the first dimension. The dimension, of, in this case, we called it BP for blood pressure. The dimension is actually a vector of length 2. And by putting a 1, it says I want the first element of that vector. And it says there are 10 rows. So there's only 10 rows. And in fact, there are 2 columns because there are 2 variables. And then I'm going to fit the model. Next time I'll step through this quickly. I just want to run through this to get you an idea because we're about out of time here. And then I plot the scatter plot. An AB line, the argument of AB line is fit BP. In other words, I have a model object, which is called an LM object, as the argument of AB line, and it pulls out the slope and the intercept automatically for you. It makes it quite simple. Quite simple. Okay, and then the only thing I'll stop here. The only thing that we now see is if I print the object by default, it prints the model and it prints the slope and intercept, which is what we just drew up here. So you can see that we can do this. There are lots of other things that we could get. We could actually enhance this graph in various other ways. We could, in principle, draw all those little vertical lines if we wanted to between the points and the predicted values. In R, you can do that kind of stuff. But it might be a little tricky. So are there any questions? Well, I suspect we'll pretty much get through the rest of Chapter 9 on Wednesday. So read through Chapter 9. Again, I'm go ahead and start on the assignment. I'm going to sort of redo it a little bit. I may replace some of the ones that have summaries by real data because I'm more interested in you. I'm more interested in it. So I may modify that assignment somewhat. But you can go ahead and begin the assignment if you want to get started. The one I sent in. Yes?
When is it due, and do you expect like some of them to be hand done, or is that like optional?
I'd rather have you use R even. I'm going to send you a template. And even if you use R as a calculator. So I'm probably going to make it a couple weeks to give you time to get used to R. Is everyone practicing R, getting accustomed to it? So even if you could do it by a hand calculator, I want an electronic submission. So rather than sort of doing it by hand and taking a picture of it and uploading a photo file, I would rather you use R as a calculator, even as examples, where you have, in other words, you could simply could say y bar sub 1 equals such and such, y bar sub 2 equals such and such, s bar. You could actually enter in those quantities and then compute the things using R as a calculator. So I prefer you to do that. But again, I'm going to replace a few of those examples with real data. So I don't know if I can get the numbers to come out exactly the same as the summaries. Because if I can generate data, but then if I compute the y bars, and they'll be a little different than what's in the book. I mean, if I do it a few times, maybe eventually I'll get close. Are there any other questions? Okay, it'll be a couple of weeks. Again, this first assignment, I'm going to give you a little more time just because you have to get accustomed to R.
Question first. I have this one, so
Yeah, you're fitting a Lois or something.
I mean, how to test the significance of this curve.
Okay. Well, it depends on the model you use. You're using a smooth.
I don't know. I just figured this should be this pattern.
Yeah.
I want to test the significance.
Yeah, it's probably not linear in that case because you got a few outliers there. But if you took that away, then there are a couple of models you could do. You could fit segmented. You could have linear segmented pieces, which Fairway's book, for example, talks about that type of model. In this type of model, you can put one of the things you can do on this. I think they give you an option of putting confidence bands on that.
Yeah, I will.
And that's probably what I would look at to get some sense.
I want to find out whether this phenomenon is significant or not. I mean, this pattern is significant or not.
You mean as opposed to fitting
straight line.
a straight line horizontal or a straight line?
But it's
You
not
want to
straight
test
line.
it as significantly nonlinear or not.
It's like
In other words, if I fit the best straight line, which would just be the mean of this, then I could test a hypothesis. I could actually get the reductions in sum of squares from this model versus a model where it's a horizontal line, which would say that it's not horizontal. If you wanted to test that the straight line is different than that, again, you could get the increased reduction in sum of squares due to that line versus the straight line. The question is how do you figure out the degrees of freedom?
No, this thing is I discover a phenomenon.
Mhm.
This thing is irregular. It should be like this, but I discover it. So
You mean it should be
yeah,
horizontal?
as you said. So when I'm
Well,
trying
then you can test that.
to, like you said, like
Well, you can get I think you can get the residuals out of these smoothing
Okay.
models. And once you have the residuals, you have the reduction due to that fit. But you can also get the residuals from a straight line. So you can compare the reductions in the two. Do you follow me? The only problem is you have to figure out what the degrees of freedom would be, and that can be tricky.
and also a question. I'm trying to writing this paper using the one you taught us. Like I want to find you reproducible research.
Mhm.
I want to put this result in my final, but I can't do it. Like I only get something like I want to put this in my R code in my result. How to do that? I tried to find out, but it's really hard. I didn't find it.
How to put R code in a
This is
well, I would
Sweet.
use a .rmw file. What did you buy the book on the reproducible research?
no, I didn't.
There's a book that I can refer you to.
I think you showed us a slide. You do with sweep like.
Yeah, S-Weave.
I
Yeah.
want to do the.
But
if
we're
I-
talking about a paper, not
yeah,
a
a
slideshow.
paper. Yeah.
I have some examples of that.
Yeah, please give me.
So yeah,
Yeah.
I can show you some examples. And there's a book I would recommend to you. I think it's called Reproducible Research Using Aura and
Yeah,
RStudio.
you mentioned about it.
That maybe I should put that as a reference in my, because it's really a good book. I like it actually better than the book. There's a book, another one called Dynamic Documents with Aura and Knitter or something like that. But I actually like the reproducible research better.
Yeah. Can you give me some result using our research?
Yeah, we could. We can. I have some example articles. I can
Okay.
give you.
I search online, but not find it.
And there's a little tutorial. There's a little tutorial that a guy does. There are a couple of tutorials out there that might be useful.
But we can present the result using this one, right? Present the result in our paper. Like, if I draw
Well,
this.
I would. Oh, in your paper or the
Like-
class? The class I,
I mean-
was going to use .rmd files, but
Yeah, I
you're
know.
talking about a .rmw file.
Yeah, I know.
Yeah.
I mean, if I include this one in the paper, can I
Mhm.
do that?
Sure. Sure, that's
Yeah,
easy.
that's how I
Do you know
find out
LaTeX?
latex. I'm learning it right now.
Yeah, you need to learn LaTeX in order to do this, but yes,
Okay.
it's easy to do.
Okay. So
Well, it's easy to do if you know LaTeX.
yeah, I'm learning it. And so
Okay.